Oh, wonderful. Okay, well, I just wanted to share the most wonderful news of the morning. Okay, this is my poor version of a printout from online. It's the Walter Cronkite National Awards for wonderful excellence in journalism, and you might see a face there that you
Mm.
recognize. It's a possibility in amongst the CNN and the Dr. Sanjay Gupta. There's a Maritza Giorgio. Congratulations.
Yeah, very good.
Thank you. Gosh, hearing you say that makes it really real. I'm very emotional and so blown away, for sure.
Well, you deserve everything that can be thrown at you. Wonderful journalist you are, and I'm so proud of you. So, congratulations and all of that over a little blue mailbox. Tell us the story quickly.
Okay, well, it started with an email from John Chester's office saying, we're hearing maybe possibly these mailboxes are being removed by the United States Postal Service, and we have reports of maybe this many in this town. And so the next day I reached out to one of my contacts who's one of the local union leaders, and I asked if they knew about it. And they sent me this list of addresses where all these mailboxes were supposed to be removed, including in front of the main Missoula post office and near the University of Montana and outside the county courthouse and outside of senior living facilities where they're not supposed to remove those mailboxes. And so I just started kind of putting all the information on Twitter and the addresses and marking where they were on a map. And it just took off, and it started to be shared by many national reporters and journalists. And I wrote all of our congressional delegation, they all wrote letters same day to the USPS saying, stop this. And by the end of the day, the United States Postal Service stopped the policy for the whole country until after the election.
Thanks to Maritza. Yay!
Thanks to the union worker who sent me the list.
Anyway, congrats. Appreciate everything you do. And let's see. Wolf is not among us at the moment, I guess. So I did have one inquiry this week, and can't recall from whom, but just be sure you're up to date on your dues membership for this year of $20, and address your many checks and money orders to Wolf Spiegler. James, back to you.
Okay, and I'll throw it back to Jack because Jack's got a story for us this morning.
This story goes back quite a ways when they used to tell a lot of North Dakota jokes. But anyway, there were three steel workers sitting up on a girder about 30 stories up, and they were sitting there eating their lunch. And the Italian said to the crew, he says, I've been getting this Italian food. He says, day after day after day. He said, I'm getting sick of it. He said, if I get that one more day, I'm going to jump off of here. And the German says, you know, he says, I've been getting this German food, this sausage all the time. He says, I can't stand it any longer. He said, if I get that one more day, I'm going to jump off of it. And the North Dakotan says, you know, I have the same problem. He said, I've been getting the peanut butter and jelly sandwiches every day. And the next day, they all got the same thing, and they all jumped off the deal. And the wives were talking at the funeral, and the Italian wife says, I don't know what was wrong with him. She said, if he had said something, I could have made him a different lunch. And the German woman said, my golly, she said, I feel the same way. She said, I got to change it. And the North Dakota wife says, I don't know why he always made his own lunch.
Okay, so I take it North Dakota jokes are like Polish jokes and et cetera, et cetera.
Yeah,
Okay,
Well, if you're not politically correct, why, you can still tell them. And that's me. I'm not really politically correct on a lot of things. So.
that's okay. We'll let you get away with it this time. Okay, our speaker today unfortunately had to pull out at the last minute. But Dick Field, who had asked the speaker to join us, has kindly stepped up to fill the gap. So I'll turn it over to Dick. You're all set to share your screen, Dick. So take it away, please. And everybody else, please mute.
So good morning, everybody. I hope you can hear me. I actually welcome this opportunity to talk with you. I wanted to give a talk this morning on thermodynamics and the steam engine, which has a lot of interesting history, but I couldn't make my computer system, which is brand new, scan things and put them into PowerPoint. The file kept getting lost. I think it's a problem with my scanner. So this is a talk that I prepared quite a number of years ago for a group much like Senior Forum at Christ the King Church. And when I joined that group, people wanted to know what the opinions of a physical scientist was on God. So I wrote them a talk on that. And I've decided to try that. I've taken most of the theology out, so it's mainly science. So let's see if I can get it. Let's see, share screen. Okay, and there's my, and okay. And then somewhere, okay, and here's somewhere around here. There's supposed to be, and let's see whether it works. Okay, so this is the title I modified, God and Science, a discussion of the relationship between God and science. And this is the date. And I'll skip all the stuff on my religious background. Start out talking about the nature of science. That's basically what the talk is about.
Dick, why don't you make the slides bigger?
Okay, let's see, hit slideshow from beginning. Okay.
Works better down at the bottom on that thing that you and I talked about yesterday. There you go.
All right, so let's see, I should be able to, okay. So here's Karl Popper, who was a famous philosopher of science, defined science as that collection of statements concerning the, concerning the physical universe that are disprovable by observation. This is a incomplete but accurate definition of science, actually, the idea of provability. I've got to move the, yeah, okay. Observation of the physical universe is the basis of science. The universe must be assumed to be entirely governed by physical law if science is to be a useful way to understand it. And that's a basic part of the whole thing. If we're going to have a God meddling with things, then you simply can't do science because you can't tell when he's meddling and when he's not, or she's not. So, and however, the interpretation of scientific observation is, like religion, a matter of faith. The basic definitions are circular. The entire structure of science is constrained by logic. And by what we are allowed to know. And I'll say more about allowed to know near the end. So let's see. Here's just some suggestions on the whole thing. I had a very fine grad PhD student by the name of Girish Kshirssagar, He got his PhD in 1989. He's now working for Google on artificial intelligence. He's a neat man to work with. I just really enjoyed having Girish around the lab for 4 years. One day he told me about the Indian rope trick. And so here's a picture of the Indian rope trick made with puppets. And in the Indian rope trick, you have the faker, this guy with the whistle. There's his assistant, and here's the rope. And it starts out with the rope being coiled up and the assistant standing by. And the faker starts blowing his whistle, and the rope starts to uncoil and to rise up. Before long, it's just a rope, straight as an arrow, standing up. And at that point, the faker's assistant climbs over to the rope and walks over to the rope and climbs up to the top and disappears. And that's the Indian rope trick. And when Girish told me about it, I said, well, Girish, I don't believe anything happens in violation of physical law. He kind of smiled at me and he said, I disagree. So I just like that story. This is a picture of the Earth, it's a pretty picture. I thought it would go with this a little bit. We had a talk at the university, kind of a faculty group who got together Thursdays and gave a talk. Somebody gave a talk, much like Senior Forum, I guess. And Fred Allendorf is a UM biologist. And he gave a talk one day. And he marshaled all of the scientific evidence for the age of the Earth as several billions of years, and the evolution of life on the planet. And he presented all of the scientific support there is, observational support there is for that idea, for the growth of the universe, the growth of Earth. Biologists, in my experience, tend to be kind of arrogant. Sometimes I think it's because they work with living creatures, they think they're God. And so Fred kind of annoyed me with his certainty about all of this. So I couldn't resist at the end of the talk asking him, Fred, if you went back to your lab this afternoon and created an Earth, wouldn't you believe your Earth was incomplete if it didn't have a history? And of course, there's no real answer. If we believe in a God, then, well, he could easily have created the Earth with all of this. So the point is that when you have a God meddling, you just can't do science because you just can't do it. So a little bit of talk about the scientific method and what laws are, and physical laws are. And for an example, what is the equation of state? That is the relationship between the number of moles, the temperature, and the pressure and the volume of a sample of a gas, of what we call an ideal gas, which basically means that gas atoms don't interact with each other and are so tiny that you don't have to worry about the volume they take up. So here's the experiment one might do. Here's a piston in a cylinder, and we decide that the pressure of the gas comes from gas molecules racing around and colliding with the walls of the container, and hence transferring momentum to the walls of the container and supplying a pressure. And so this is a model we have of this particular this particular system, that basically there's a pressure exerted on this container, and we can contain that pressure with a piston, and the pressure is supplied by atoms flying around. That's what we call a model of this system. And so you do experiments, you can apply some pressure to the piston and see where it moves to, and that's the equilibrium volume. And so you can plot the pressure and the volume on a graph, and then you can change the pressure, and that squeezes everything down and the pressure increases. And so one can take this pressure and that volume and put it on another spot on the curve. And at the end, this is the curve you get. So that's basically the experimental data that we have for this system. And a physical law? Well, from these experiments, we deduce the physical law that the pressure times the volume is always equal to a constant. And this constant, oops, goodness gracious, this thing is really sensitive. C depends on, and the constant depends upon temperature and number of moles. And we can generalize this to the physical law. PV is equal to nRT, which you've probably all heard about. And so here's PV equals C. We can divide through by the volume and by the pressure, and we can get the volume is equal to 1 over P times the constant. And you get a nice straight line. And physical scientists just love straight lines. That means that basically what you're doing is correct, or at least fits the data. This work was done initially by Robert Boyle, 1637, 1691, and his father was the Earl of Cork. And I show the picture because my wife, a professional genealogist, tells me that his brother was probably one of my ancestors. So they were Irish, of course. So this is the idea of a physical law. It's just we've taken some observations and we've just fitted them to some kind of an equation, and that equation is basically the physical law. So let's see. The interpretation is elusive. We assume the pressure exerted on the walls of the container results from gas molecules racing around at very high speeds. They go faster at higher temperatures, and the fact of the matter is that's the way we define temperature, is what is the average kinetic energy of the molecules and colliding with the walls. With this assumption, we can deduce by counting on our fingers the ideal gas law. I remember as a graduate student when Professor Krauss started out counting on his fingers, basically setting up the statistical mechanical treatment of the whole thing. At the end of the class, he had derived this physical law basically simply by counting on his fingers and assuming that there are molecules in the system. This is the kinetic theory of gases, which is attributable to James Clerk Maxwell, who was probably the first theoretical physicist. He worked in the late second half of the 19th century. So the idea also is we can test it as well. By testing, we can now look for deviations from ideality. That is, these occur at high pressure, where the molecules are close together, and so their attractive forces become important. And at low temperature, where they also get closer together, and the attractive forces become important. Can we interpret the deviations on the basis of molecules? Yes, we can interpret the deviations on the basis of molecules. Can we prove the existence of molecules? No, we cannot. We can only fail to disprove our assumption. That's another one of the, probably the most important point, is that we can't prove things in science. We can only fail to disprove them. So, what's next? Disproving and proving a theory. As I say, science is composed of statements subject to disproof by experiment. Failure to disprove a statement by experiment does not prove it, because we may not yet have done the correct disproving experiment. Or there might even be an alternate theory that rationalizes the physical law equally as well. So we really can't say a theory is proven. Simply, we test it so many times that eventually, just like we know if the sun comes up every morning and expect thus for the sun to come up every morning, eventually we begin to believe these things, but they're not proved in any logical sense. The only way that you can prove a theory is within an axiomatic system, and the proof is only as good as are the axioms, our assumptions. So the idea here is one has a system, and you write down several assumptions, axioms, that you believe to be true, And then from these axioms, then you can apply the laws of logic, and you can deduce things. And within the correctness of your axioms, then your result is proved. However, there are problems with axiomatic systems. This is a couple of pictures. This is Kurt Gödel, who in 1931 introduced the incompleteness theorem, which actually developed by a bunch of mathematicians and logicians in the coffee houses of Vienna. And Gödel came to Princeton, and that's where he did his best work. I show this picture of Einstein simply because all we see is that crazy pictures of him with his hair flying. Well, this is what he looked like in 1926 when he did his greatest work, his miracle year. He was a good-looking young man. And when I used to teach physical chemistry, one morning I would show, every morning I showed the class some photographs of an important person involved with the history of whatever piece of chemistry we were going to look at that morning. And I'd try to show a picture of them and give some theory about ideas about the person himself or herself, and also some idea of what problem it was, what observation it was that caused him to make his discovery. The students absolutely loved it. I used to like to show also a picture then of my grandfather and my mother, and point out to them that that picture was taken in 1911, and that my grandfather was born 4 years before Einstein, and that my mother was contemporary with the people who developed quantum mechanics. That gives some perspective to how long science has been going. So in any case, back to Gödel. He and Einstein were best friends because they both believed science actually describes a physical reality. Gödel even proposed a mathematical proof of the existence of God. They both believed that there is a true physical reality. It is not just what we see, but there is a true physical reality out there. There are actually physical things moving around that produce the observations. And both Einstein and Gödel believed in this idea that there is a true physical reality. I'm suspicious, I'm not sure there is. Any actually, at least at the microscopic systems, atoms and molecules. Gödel's theorem is the following. Any axiomatic system that is strong enough to allow proof of everything we know by observation to be true will also allow proof of at least one thing we know by observation not to be true. The problem is contradictions that develop when you set up axioms. There will be some questions that are unanswerable without further information. Thus, the logical system is incomplete. That's why it's called the incompleteness theorem. The classic example is that somewhere, many people often say it was Princeton, New Jersey, where Einstein and Gödel both worked. Many people say that it was a barber in Princeton, a male barber in Princeton. And he had a sign in the window of his barber shop, and it said, so-and-so the barber is willing to shave any man who is unwilling to shave himself. And the story is further said that Gödel walks into the office and says, are you willing to shave yourself? Because that question is unanswerable under that axiom. How can you answer it? And so this logical system is incomplete. We have to put in more information to actually figure out what's going on. So that's the incompleteness theorem, which is profound. Okay, can physical reality be visualized? It was a big argument among late 19th century scientists was, are models actually accurate representations of physical reality? Is there an actual physical reality Can we visualize it? Or are these models simply something that allow us to produce equations that match observations? Is there really something behind them? One of the major scientists, one of the major scientists, in this era was Lord Kelvin, whose real name was William Thomson. He was a Scotsman. He was an extraordinary physicist and dominated late 19th century science. Lord Kelvin demanded that mechanical models of physical realities. He demanded that mechanical models of physical reality be used to express scientific ideas. You had to have something you could see, gears and pulleys and wheels, stuff like that. That's what he demanded of mechanical models. He even demanded James Clerk Maxwell, when he came up with his electromagnetic light theories, deduced from observation of electrical magnetic properties. He even demanded he express that model, which Maxwell deduced by simple manipulations. He demanded that there be a physical model connected to it. Well, James Clerk Maxwell was one really, really smart cat, and he was able to do that. I have a book called Kelvin. It's a story of temperature, basically, but it really is a story of 19th century physics. In those years, they really had no idea what was going on. They just found a little piece of the elephant and described it, but they had no idea that there was an elephant there, basically. And so the author of this book said he would like to go back to that era and talk with the people, scientists who were working at that time, and tell them, well, this is the way it turned out. This is the way reality that we understand now, or the world as we understand it now, is put together. He said he would do that to all of the scientists except Lord Kelvin, because he would not have been able to accept that in the end, there is nothing but mathematical abstraction. That's certainly true in microscopic physics. It's pretty much true elsewhere as well, but not nearly as obvious. Lord Kelvin was quite a guy. He made a lot of mistakes because he didn't know the elephant was there, basically. But he suggested the idea of a transatlantic telegraphic cable. He designed the cable itself. He designed equipment to detect very weak electrical signals, because after traveling across the Atlantic, electrical signals were pretty weak. He actually capitalized and oversaw the construction of the transatlantic cable. Made quite a bit of money on it, I gather. The British Admiralty had a lot of battleships, and when they were all wooden, it didn't bother the compass very much. But when they started having big cannons and steel ships, then the compasses just went crazy. And so the British Admiralty appealed to Lord Kelvin, fix this problem for us. And he did. He built a compass that was compensated for the amounts of metal in its vicinity. And the British Admiralty used that compass until really quite recently. He is wrong sometimes. He he started out by saying the Earth was a ball of molten rock at the temperature of molten rock, and that molten rock cooled by radiation, that is electromagnetic radiation, believing taking energy with it, and that the Earth cooled by that. And he calculated how long it would take for this ball of molten rock to cool to the temperature of the Earth we see today at the surface anyway. I came up with 100,000 years. Some people complained that it was 6,000. The geologist said that rock has been out in the rain a whole lot longer than 100,000 years. And so the idea wasn't really accepted. But eventually he did so many things. He was one of the founders of the idea of temperature, that he was made a peer, a British peer, a lifetime peer. And so he had to choose a name for his peerage. He worked at Glasgow University in Scotland. And he was talking with his wife about it. His wife said, well, you know, Bill, there's this creek, Kelvin, that goes through the Glasgow campus. And the Kelvin Creek is just like what you do. The creek goes through the campus and then spreads around the world. And your ideas begin in the campus and spread around the world. So he adopted the name Lord Kelvin, which of course, finally the temperature scale was named for. So if you ever wondered where the name Kelvin came from, that's where it came from. So getting close to the end, images of benzene. We deduced many, many years ago, late 19th century, when only organic chemists believed in atoms and molecules. They deduced that benzene is a circle of 6 carbon atoms bonded together. Each one of the carbon atoms has a hydrogen atom bonded to it, and there are clouds of electrons around in here. And we knew all that. This is a picture that's been taken fairly reasonably. These are benzene rings here. We can't see the atoms. This white area is probably where the electrons are. And we can actually watch this particular molecule react to give you other molecules. So this is what the thing looks like to begin with, and it can just decompose, or I guess must condense or rearrange to give you these 2 molecules. So these are the first high-resolution pictures of a molecule breaking and reforming bonds. The pictures show that we were remarkably good in our deductions from very obscure data that we actually came to these conclusions. The model. We cannot visualize what goes on in the white areas. That is, we can't see electrons flying around in there. We can't visualize it. And the reason for it is that electrons have a very peculiar property. You'd think they were a particle, a little particle of charge. They have a mass. And you'd think that if you did an experiment to test the molecular, whether or not the electron was a particle, it would turn out to be a particle. On the other hand, if you thought the electron was a wave, just like a wave you get when you drop a rock into a pond, if you thought that might be what an electron is, and you did an experiment to show whether it was a wave, it would look like a wave. This is called the wave-particle duality. It is completely beyond our ability to visualize what exactly that must look like in terms of the things we see in our everyday life. It's not visualizable. And eventually, a fellow by the name of de Broglie has an interesting history too. One of his ancestors built a whole bunch of cannons for the French king, and so he was a nobleman and had a title, which I'll show you next slide. In any case, he said that for an electron, it has a wave associated with it. This is the wavelength of that wave. It also has a momentum associated with it, such as a particle has. This is the momentum. This is Planck's constant, which is a fundamental physical constant. And so this is called the wave duality equation. It's a contradiction. Every place we use it, contradictions appear. It's amazing, it really is. So incompleteness, back to incompleteness. So our knowledge must be incomplete concerning both the physical universe and perhaps to the extent the laws of logic apply to our knowledge of God. However, let's see, here's the photograph of Prince Louis Victor Pierre Raymond, 7th Duke of de Broglie, 1892 to 1987. So he lived for 95 years. And when he died, his brother took over the dukeship, his younger brother. So in any case, from his suggestion that lambda is equal to h over mv, the electrons of both particles and waves, another gentleman, actually he wasn't a gentleman, he was a bounder and a cat, Erwin Schrödinger. This is a picture of Schrödinger when he made his great discovery or invention. And of course, we do debate whether he discovered wave mechanics or he invented wave mechanics. That's something people talk about in the coffee houses in Vienna. And he, from the this equation lambda is equal to h over mv, he deduced this equation, which is called the Schrödinger equation. This describes all atomic and molecular systems. It is so good that often things that you want to know the value of, you'll calculate them from this equation because the equation is more accurate than an observation would be. So it's a really good equation. The problem with it is these little psi's here are probabilities. We don't know exactly where the electron is. We don't know exactly what it's doing. We just have probabilities. And so this is a form of incompleteness. We don't know everything because of the probabilistic nature of this equation and presumably the probabilistic nature of the least microscopic universe. And so what I said earlier, that all those things that we are allowed to know, while we are not allowed to know the position and the momentum of an electron at the same time. We can know one or the other. We can know probabilities, but we cannot know the position and the momentum at the same time. And so this is the elder Schrödinger. That's the younger Schrödinger. There's a story about the invention of wave mechanics. Erwin Schrödinger was an incredibly brilliant man. He was particularly good at explaining science in ways that people could understand it. And so he was often asked to present seminars on something that was of interest to his colleagues. And so he was asked to give a seminar on the de Broglie equation. And I won't say much about the seminar itself, but it was a really nice seminar. And in the end, de Broglie, Schrödinger talking about the wave nature of the electron. According to the story at the end, oh goodness, my memory has failed me. What was his name? Oh goodness. Famous physicist from Munich, Peter Debye, I think. Yeah, Peter Debye walked up to him after the talk and said, well, it's an interesting idea about how you can apply the de Broglie relationship to atoms and molecules. But I did my PhD work with some other guy, and I can't remember his name. This is terrible. It's getting worse and worse. A professor at Munich. And he told me that if you're going to be dealing with waves, then you've got to write down a wave equation. So Schrödinger wrote down the standard wave equation of physics. He plugged in the de Broglie relationship, and this is what came out. As soon as he heard, apparently, Peter Debye, he realized Debye was right, correct. So he called one of his lady friends at the moment, and it was just before Christmas break. So the two of them took off to a guest house in Switzerland, and among other things, I guess, he invented quantum mechanics there. So in any case, that's all I have. This history of all these things is really interesting. I'd be anxious to, if we have time, answer any questions anybody might have. Let's see if I can get rid of this. Ah, there it is. Okay. Oops.
Any questions or comments or? You know, Dick, I think you could have just made up those names you forgot and nobody would have corrected you. Gary?
Yeah.
Hey, good morning, Dick. Many of your things go just like this over my head, but I have a question. Why was there so many people in Germany and Hungary, Austria in that era that were brilliant scientists?
That's a really, really good question, Gary. I sometimes think that the boom of science in Europe resulted from the combination of Jewish imagination and Prussian discipline. It came from the culture one way or another. The nobility was important because these were people who were smart enough to become nobility and had time on their hands and lots of money. I think that played a big role. Many of these people were Jewish. Many of them came from very wealthy families. And particularly in Hungary around the turn of the 20th century, there was a gymnasium in Budapest for German-speaking Jews went to it. It was actually a Lutheran gymnasium, which was closed by the communists, is now open again. And this gymnasium had a math prize every year. Over the course of a number of years around the turn of the century, 5 of the most famous, powerful scientists of the 20th century won that math prize. Some of the names would be familiar to you. A fellow by the name of Szilard. He was the one who prompted the writing of the letter to Roosevelt about the atomic bomb possibility. Turned out the British physicists had gotten to the MIT physicists and they had gotten to Roosevelt. He knew all about it by the time he got the letter from Einstein. William Teller, the founder of Star Wars, was a member of this group. Von Karman, who eventually founded the Jet Propulsion Lab, was a member of this group. Eugene Wigner, who was one of the founders of quantum mechanics, was a member of that group. So was John von Neumann, who was in the running for the best mathematician of the 20th century, through this gymnasium. So that suggests to me it's cultural in nature. I don't think that those people are any smarter than other people. I think they just happen to be at the right place at the right time and have the time and the money. So that's the best I can do to answer that question. I hope it's.
And then I had one more question. Your second slide, Einstein and Cabell, is it?
Gödel.
He obviously must have become mentally ill. Didn't he starve himself to death or something?
He was a very strange chap. Yes, he was. There was a fellow by the name of Gödel on Jeopardy some years ago. And he looked like Gödel, the famous one. I wondered whether it was his great grandson or something, but he was a strange chap, and I believe he did have emotional problems. Einstein, of course, had no emotional problems. That was his great strength. In the end, there were other physicists around, we believe, that were just as good physicists as Einstein was. They did not have Einstein's personal and mental discipline to keep working on the problems. And that was what I believe, set him apart from his contemporaries.
Okay, thank you.
Any other questions or comments? May?
First of all, I'd just like to say I hope that all of the students that had you understand the gift that they got by being in your class. What a fascinating place that must have been. So congratulations on your career. My question has to do with our current posture, I guess, about the questioning of science. And clearly, logic is not going to be the way to convince people that the science is a good thing to follow in terms of the vaccine. How do you approach those issues when there are questions about the science and there's not a logical way to convince people that it's okay to follow the science?
I think we could fundamentally fundamentally change our educational systems to emphasize thought, because I don't think we're doing that now as well as we might. I guess that's the only thing I can think of. I think the people who don't believe in science are fearful. I don't know how we can cure that. They're fearful of what science is going to do to them. Science is going to make them do things they don't want to do. I think it's a matter of education, I guess. That's all I can think of. Most people that it's very rare. I tend to be very intense sometimes talking with people. And I find that if you do it in a friendly way, you often can convince people who seem to be unconvincible. But it's a tough road to hoe, and it's getting worse and worse. The idea of right. We have a problem with right, I believe. Because people forget that every right has a responsibility, and every person has rights, and often these rights contradict each other, or well, your right will violate somebody else's right. I think that perhaps some dealing with rights and responsibilities might help too. That's all I can say. That's one of those questions.
Jim Harmon?
I'm curious about a few things. One is science is good at disproving things. Is that my takeaway?
Science can only be, a scientific statement can really only be disproved. We can't really prove in the sense that we can prove that 1 + 1 is 2.
So out of that, is there any scientific investigation, project, anything into the question of God?
Yeah, I think that there was. I'm not sure it's still going on. Gödel, of course, as I mentioned, did claim to have a mathematical proof of the existence of God. I don't really know. There are a lot of there's philosophers of science. There is a lot of some academic work going on. I don't really follow it, so I don't really know. So back in the 19th century, there was a lot of interaction. The 16th, well, the original scientists were natural philosophers, and they were mainly actually religiously trained. So in the beginning, they were quite closely linked, and people discussed the relationship a lot, I think. But I think finally they gave up. So
I was
that's
curious also. The human mind is at one place in development over the eons, and science is speeding ahead. is there a possibility that science and its speeding ahead leads to the doubters of science? That the human mind just hasn't developed enough to be where science is today?
I believe you are correct in that statement, actually. We just, it's absolutely I started seriously looking at science in late 1950s. When I look back at what we knew in 1958 and what we know now in one career, it's utterly shocking. CRISPR is going to allow us to actually change human nature. CRISPR is the gene editing program, gene editing experimental method. We can literally change human nature. We can reach into the gene that makes a guy a son of a bitch, put in the nice guy gene, if we wish. On the other hand, we might do the opposite.
Let me know when that's available for me.
I believe CRISPR will eliminate cancer, provide cures for cancer quite soon.
Bill?
Yes, this question goes back to Gary Hughes's question, talking about the culture that existed around the 1900s. Is there any place in the world today where that has a similar culture that spawns that sort of discovery?
There's a problem in physics. It's called the many-body problem. Many-body problem. If you have two particles, you can precisely mathematically describe the interaction of those two particles. If you have three, you cannot. Mathematics doesn't know how to do that, or we have to use numerical methods. And I was talking with somebody about the solution of the many-body problem, and the person said it will probably be solved by somebody who is a youngster in China. I think the Chinese have a good chance of, there's so many of them. They are fairly academically oriented, and I think that's probably the best chance we have to recreate something like that. So somebody's going to figure out the problem. It's probably going to be a Chinaman.
Jack? You've got to unmute yourself, Jack. There you go. Oop, no, you're still mute. There you go.
Now can you hear me? Yeah. Science doesn't have any end. It just goes on, and things that spin off from scientific work is what makes life livable, and we improve. At least we think we improve from all the things that the science has done for us. But if you look, it gets better as the time goes on, but it'll go on forever.
I hope so. My computer has gotten so complicated that really I can't do simple things on it. I don't know what that means in terms of your question of continuation of science, but I hope that it gets better rather than just more complex or bigger or better. I hope it gets better, not just. There's a theory about how things work. I think it involves giantism. And it says if you have something you want to do, like say you want to create pleasing music, then you will work toward pleasing music. And in my opinion, the work toward pleasing music culminated with the classical era in Europe. That's my personal opinion. Once they got to that, what did they do next? Well, they tried, all kinds of different things came up. Some of, who knows whether they were good or not. And the same thing happened in painting, I think. Painting is to show an image. That probably reached its climax in the Dutch masters. And then we got modern art. Whether that was going to happen, that's basically what happened to my phone, actually. So I don't know whether that pleases you or not, but I think it is the nature of things to go through this. It's called giantism, and you just try to make it bigger rather than better. So I hope that we go the way of making it better. I don't know whether that's a reasonable reply, but that's what
Okay.
popped up.
Anyone else? Dick, thanks very much for stepping up and giving an interesting talk.